Engineering 305. This is problem 826. Now, I've already solved this once. I think it was a special request by someone, whatever. But I want to go back and do this now. Now what we know later, and maybe we should even do this with singularity functions. But yeah, we can we don't want to solve everything 3 times. So. But I do want to revisit this and attack it again with the new superposition technique that we're using with these cartoons. So, excuse me. So here we go. This is cantilever beam shown in ABC. It has a second moment of area 2I in the first half and I in the second half. Determine the deflection at section B and the deflection at section C. All right. So the first thing I'm going to say is, that becomes a challenging problem by itself, but because it's symbolic and we have 2I and I want to get rid of those. I think that just leads to mistake. So I'm going to say that R is equal to 2I, and I'm going to say that T is equal to I. Yeah, now those are my initials, but that's how I'm going to keep this straight. So that's R and that's T. And so we don't have to worry about that moving forward. So let's start breaking this down. So in the last video, I know because I just did it, I took this cantilever beam that has this load and this load, and I said, okay, how do I break that out? Okay, so that is going to become this beam with I'm going to transfer this force to here. So I'm going to have a load and a moment on that, and then I'm going to have another cantilever beam, and now it's actually a cantilever beam here that goes out and has another load P. But I'm going to say that's fixed, except that I've already got some twist going on. I've already got some angle there, because if I think about this becomes a beam that looks like that, and then a beam that goes like that. And so this has this load and this moment at that point. And that's going to... So here's where this becomes really complex. That becomes the deflection. It's like the last problem. I've got a deflection from the point load. That's my first term. I've got a deflection from the moment load. And I think I can pull up, I look at a cantilever beam and I've got a deflection from a point load and a deflection from a moment load. So I can solve both of those problems. But then I've got both of those get a twist at B. And so this is the twist at B, or the slope at B, times the length out to the end. And I've got to say the twist at B from the point load, and I've also got a twist at the end, a twist at B from the moment load. Both of those are occurring, and so then I've also got, and then that gets a length to the end. And then lastly, I've got the deflection of C relative to B. I should say this is from and that's just from the point load on the end. This is the deflection at B. That's the deflection at B from the moment load. You see how all 5 of those terms show up? Yeah. So now we got to start walking through all of this. The first thing I still need to do is I've got this and this, P, this is L, this is L. I've got, well, no, that's what I need to know. So when I look at this first term, delta is equal to, and if I go to my equations, PL cubed over 3EI, it's negative PL cubed over 3EI, negative PL cubed over 3EI. but now I have to translate everything. That's what it is in a normal situation, but now all those symbols might mean something else. What is my load? What is P in this case? Well, if this is, I'm going to start putting some notation down here. This is B from the point load. P is actually 2P because I have both of those. That load has to get moved to there to solve that first problem. So that's a minus 2P. Is L actually L? I got to go back. Yeah, L is L. L cubed over 3E. Young's modulus is Young's modulus. But this is R. The I for this section is R, or it's equal to 2I. I'm just going to put it as R for right now. All right? We'll substitute that out later. There's my first term. I'm going to write it in red because these terms I'm using the wrong variables. I'm going to look at that equation. So this is now going to be the moment. This is the deflection based on that moment. Well, what's my well, okay, so that deflection, we'll write the equation down, is ml squared over 2EI. And now it's positive because they're showing me a positive moment. My moment, that's my moment, right? So it's a negative moment, so it's going to be a negative ml squared over 2EI. ml squared over 2EI. I guess I'll get rid of that because I know my moment is going to show up as negative. That moment is equal to P times L, right? When I move this force to here, then that's how I got the 2P, but this now moment is equal to PL. Okay? So that equals, and it's negative. So now I've got a minus PL times L squared over 2E. It's not I, it's R. All right? Now you can see my units work out. I got a PL cubed over 2ER. Here I've got a minus 2/3 PL cubed over ER. So that's kind of okay. So my units are working out. Okay, let's keep plugging away. I'm going back to red because these aren't necessarily correct. This is theta at B, the twist at B, as a result of the point load, and then I got to multiply it by the distance to the end. So that's B from the point load, B from the point load, sorry, yep. B from the point load is equal to sorry, that's not what I want to write. The term that I'm trying to solve is theta at B from the point load times the length out to the end is equal to, and I'm going to go back to my equations, that theta is minus PL squared over 2EI, right? Minus PL squared over 2EI. And then the length to the end. Now you see I've already got L and L, so I should have put end, and I should have put of the cantilever beam. But that's why those are all in the wrong terms. Now I'll write them in the right terms. What's the load? Right away the load is actually 2P minus 2P. That's my load. My length is L squared. I'm going to divide that by 2E and then R. My section modulus is R. And then I write that a length to the end. And actually, L is L. The first L equals the second L. So at least we got that going for us. All right. Third term. Theta from the twist from the moment. Angle at B from the moment times the length to the end is equal to, now pull that one up, ML over EI. That's the twist at the end. Equals ML over EI. All right. And now my moment is equal to PL, but it's in the negative direction, so it's minus PL, that's the moment, times L, divided by ER, and then I have to multiply that by the length out to the end. Now, if you looked up here, we had PL cubed over 3ER. Here we have PL cubed over ER. So we're still matching our units up. We're still good on that front. And now I'm down to one term left because the only term left is this deflection of this very end section, which is the deflection of C relative to B due to the point load out at the end. And that's delta of C relative to B because of the point load is equal to, now can you write this one down from memory? 3E, but now the section modulus is T. Oh, I'm just going to put it, sorry, I jumped ahead. It's EI. And now I have to substitute the right terms. Minus P. L is equal to L, but now it's 3E T. And I'm writing that down. There's my equation. You can see the PL cubed over 3EI. Center of the top, line 1. Yeah. All right. Okay. Shrink that a little bit. You can see all 5 terms at once. So if I start writing them down, I think you should realize there's going to be an EI kind of term come out front. Maybe what we should do is say that R is equal to twice T, or we should go back to I. I don't know. Why don't we just go back to, we'll go back to putting this into terms of I. Hold on. Excuse me. We'll just start doing our algebra. My total deflection is equal to minus 2PL cubed over 3ER minus 2PL cubed over 3ER. You know, I'm going to have a PL come out of this too. Actually, I'm going to do that. I'm going to start collecting that. I'm going to have a PL cubed over E come out. And so that's minus 2/3 R. Minus 2/3 R, or sorry, minus 2 over 3R. Minus, and then, okay, my second term is right here already. Minus 1 over 2R. Minus 2 over 2 cancels, so it's a 1 over R. Minus, that doesn't have the 2's to cancel, so it's just a minus 1 over R. And then this last one is minus 1/3 over R. PL cube, PL cube, PL cube. There. Oh, sorry, it's not an R. You guys were lit. T. So I am going to substitute in a 2I for R. So I probably times minus, so I'll put the I out front, so everything gets just R becomes 2I, so everything gets divided in half, so it's minus 1/3, minus 1/4, minus 1/2, minus 1/2, minus 1/3, because that T is just equal to I. So I guess I have to go to twelfths. Which is PL cubed over 3E. Sorry, it's not 3. That's my cantilever beam formula that I love so much. Over EI times 12. So minus 4. I'm even going to put my 12 out here. minus 4, minus 3, minus 6, minus 6, minus 4. That's 7 and 12 is 19 is 23 twelfths. Minus 23 twelfths PL cubed over EI is equal to delta. Now, is that better or worse? The key distinction there is whether you do the integration and then you've got to solve for four different constants. Because it was a cantilever beam, the first two dropped out easily, but then you actually would have to plug in to find the deflection at B, if you recalled, so that you could use that as a boundary condition for the second half of the beam. It was a nuisance, but we got there. This requires a little bit of creativity on the front end to kind of rearrange that and make it work. They both wind up, when you're all said and done, at the same spot, but there's differences, and there will be advantages and disadvantages. That's why you set yourself up with different tools, sometimes so that you can evaluate the same problem two different ways and see if your answers agree, like we're doing with our cantilever beam lab, where we're doing FEA, hand calculations, and then experiments in the real world. So anyway, I hope you're doing well. Don't worry, there's more to come.